So another example, the odds in favor of an event A are 3:4. The odds against another independent event B are 7:4. What is the probability that at least one of the events will happen? So we want to find the probability of at least one of the events. That means to find probability A union B. Now first of all see the definition of odds. The meaning of odds, you can say. Now if A be any event, then odds in favor of A are A is to B. It means that probability of A equals to A upon A plus B. Similarly, odds against A are A is to B. That implies probability of A equals to B upon A plus B. Now in the question it's given that odds in favor of an event A are 3:4. That means probability of A equals to 3 divided by 3 plus 4, that means 3 upon 7. And it's also given that the odds against another event B are 7:4. That means probability of B equals to 4 upon 7 plus 4. That means 4 upon 11. Now what to find? The probability of at least one of the events. Now as the events are independent, it means that probability A intersection B equals to PA into PB. So this is 12 upon 17, and we want to find probability A union B. Just simply apply the addition rule, PA plus PB minus PA intersection B. Here the events are given to be independent, not mutually exclusive. So we use this one, PA plus PB minus PA intersection B. And PA intersection B we have already found out, 12 upon, sorry, what is this? Yes, 12 upon 11. So the result comes out as 7 upon 11. See this example. A salesman has a 80% chance of making a sale to each customer. The behavior of successive customers is assumed to be independent. So this is one information that behavior of successive customers are independent. Now if two customers X and Y enter the shop, what is the probability that the salesman will make a sale? Now see, to find the probability that the salesman will make a sale. Now when the salesman will make a sale? Either if either he sells to X, or if he sells to Y, or if he sells to both X and Y. So here what happens? X and Y, that means sales to X and Y are not mutually exclusive, because the salesman can sell to both the customers X and Y, but they are independent, it's given. So the required probability, how to find out? We just declare two events A and B. A denotes the event sales to customer X, and B denotes the event sales to customer Y. So required probability will be PA union B. Now PA union B equals to PA plus PB minus PA intersection B, or you can write this way also, PA union B equals to 1 minus P A bar intersection B bar. Now P A bar intersection B bar is written as P A bar into PB bar. We have already seen that if A and B are independent, then A bar and B bar also independent. This is the easiest way to find. You can use that one also, PA union B equals to PA plus PB minus PA intersection B. Then you may write PA intersection B equals to PA into PB. Or you can use this way also, PA union B equals to 1 minus PA bar B bar equals to 1 minus PA bar into PB bar. Now how to find out PA bar? It's given that PA equals to 80%. 80% means 80 upon 100. So what will be PA bar? 1 minus 80 by 100. Similarly, PB bar equals to 1 minus 80 by 100. Just put the value and get the result. You see, a problem is given to three students, Ram, Rahim and Joseph. The probability of solving the problem by Ram is 1 upon 2, by Rahim 1 upon 3, and by Joseph 1 upon 4 respectively. To find the probability that the problem will be solved. So when the problem will be solved? If at least one of them solves the problem. Now I declared the events. A denotes the event that the problem is solved by Ram, B denotes the event that the problem is solved by Rahim, and C denotes the event that the problem is solved by Joseph. Now what to find? To find the probability that the problem will be solved. And the problem will be solved, as I told you, when at least one of them solves the problem. That means to find probability A union B union C. Probability of occurrence of at least one of the events A, B and C. Now you can use this formula also. And if you use this formula, you see A, B, C, they are independent. A and B independent, B and C independent, C and A independent, A, B, C also independent. Why they are independent? Because the problem is solved by independently. They are solving independently, so the events are independent. Or alternatively, you can use this also. Just draw a Venn diagram. What to find? To find probability A union B union C. Now see in the Venn diagram the area A union B union C. This is the area A union B union C. The white region or the blank region, this is the A union B union C, and this is nothing but S minus the outside area. And what is this outside area? The horizontal lines that you see, this outside area is nothing but A bar intersection B bar intersection C bar. So I can write A union B union C equals to S minus A bar intersection B bar intersection C bar. Then take probability both sides. Probability A union B union C equals to PS minus P A bar intersection B bar intersection C bar. And what is PS? PS is nothing but 1. So 1 minus P A bar intersection B bar intersection C bar. And as A, B and C are independent, so A bar, B bar and C bar also independent. So you can write this compound event as their products and get the result. See another theorem. If A1 and A2 are mutually exclusive events, here it is said that A1 and A2 are mutually exclusive, but nothing is said about their independence. We don't know whether they are independent or not. We simply know that they are mutually exclusive. And it is given that A1 union A2 not equal to 0. Not equal to 0 means they are definitely greater than 0. What is A1 union A2? Probability of occurrence of either A1 or A2, but both parts will be excluded because they are mutually exclusive. Now to prove that probability A1 given A1 union A2 equals to this one. So first of all, what you do, we draw a Venn diagram. Now you see in the Venn diagram, this is A1 and this is A2. But in this Venn diagram, we do not show any common region because A1 and A2 are mutually exclusive. So as they are mutually exclusive, these two sets will be disjoint. They do not have any common area. So be careful in drawing the Venn diagram. You see the question at first, what is said in the question, then you draw the Venn diagram. Now once you draw the Venn diagram, then we get the result very easy. You see, just here we apply the definition of conditional probability. Probability A given B. Probability A given B means probability A intersection B divided by probability B. So probability A1 intersection A1 union A2 divided by probability A1 union A2. Now what is A1 union A2? You use this way also. You can break up this way also, and or simply you see the Venn diagram. Which area is A1 union A2? A1 union A2 means the region A1 and also the region A2. And if with A1 union A2 we take the intersection of A1, then what remains? Only A1 remains. You see, we get the result A1. Or you can break this way also. A1 intersection A1 union A1 intersection A2. We have shown this in the algebra of sets or algebra of events. You can break up this way also. Now what is A1 intersection A1? A1 intersection A1 means A1, and A1 intersection A2 is phi. They do not have any common area. And what is A1 union phi? A1 union phi is again A1. That's the result. See, if A and B are two independent events such that PA greater than 0 and PB greater than 0, strictly greater than 0, then A and B are not mutually exclusive. That means the two independent events cannot be mutually exclusive if the events are possible. Possible means strictly greater than 0. They happen with some kind of certainty. May not be with full certainty, but possibility is there. So if the two events are possible, possible means PA greater than 0 and PB greater than 0, and if they are independent, then they cannot be mutually exclusive. Now, as it is given that the events are independent, so definitely their intersection is a phi and their probability becomes 0. A intersection B equals to phi. Sorry. Sorry, I come up again. I assume that they are mutually exclusive. So let A intersection B equals to phi, or probability A intersection B equals to 0. Now, as it is given that the events are independent, that means PA intersection B equals to PA into PB. So PA intersection B, that equals to PA into PB. That means PA into PB equals to 0, as they are mutually exclusive, which implies that either PA equals to 0 or PB equals to 0. That means PA dot PB equals to 0 when it is possible, when either PA equals to 0 or PB equals to 0. But that contradicts the theorem, because in the theorem it is given that PA strictly greater than 0 and PB strictly greater than 0. Hence, A intersection B equals to phi, that is A and B, hence A intersection B not equal to phi, that is A and B are not mutually exclusive.